This is a lesson on angular momentum in the momentum and rotational dynamics units. I wanted to start with a brief overview of all the principles that you cover in the basics of classical mechanics. First begins with the basics of motion, definitions of distance, displacement, velocity, speed, acceleration, as well as the kinematics falls in here. Then it moves on to the laws of motion, Newton's first, second, and third laws, and how to use those, what the implications are. Then transformations of energy, all the work and energy considerations is one whole big topic. Then there's conservation of momentum, this idea of momentum, what momentum is, both linearly and angularly. We've covered the linear so far. So now we're looking at the angular, and angular momentum gets its own series of lessons, just like linear momentum. I will talk about the definition of it, how it interacts with torque and impulse, and finally, how it interacts with collisions and energy. Just like linear momentum is an inertial term times a speed, and notice that we can have a total momentum for an entire system, and because momentum is a vector, we can have x and y and z quantities. Angular momentum is also an inertial term times a speed. There's two ways that we think about angular momentum, and that's in terms of a point mass as opposed to an extended rigid body. Okay, and I put those over here. If I just have a point mass here, and it's moving through space with some velocity or momentum, right? Momentum is just mass times the velocity vector. The technical definition is r cross p. That's a calculus-based version. When we simplify this for algebra, we see that there's an r, a mass, a velocity, and sine of the angle. And this angle is defined to be between the radius vector and the momentum vector. So you can see that in the diagram here. This is the angle phi. We call this Greek letter phi. So if there's a point mass, that's the equation we use, and we can see that it's moving through space with some radius from some center of motion. With rigid objects may spin about an axis, and we can see that both with this disc and with the stick. It may spin in some way, and that gives us the equation I omega. Each one of these objects has a moment of inertia, and each of them is spinning with some angular speed, and that gives our angular momentum. For both of these situations, both with the point mass and with the extended rigid object, to find the direction of this L vector, the angular momentum, we use right-hand rule. And so for me, it's very intuitive, and you can see that in here with angular momentum, that I will be curling my fingers in the direction that it is rotating, and the thumb will be the angular momentum vector upward. I'm going to take a second and note that it may seem weird that angular momentum is denoted with an L. Units of angular momentum are, and notice when I just multiply this out, I have meters, kilograms, meters per second. And you can see that here, kilograms, meters squared over seconds. This is a perfectly acceptable form of the units. An alternative form, knowing that a Newton is a kilogram meter per second squared, then this simplifies to newtons times meters times seconds. And those two are equivalent units. I have no preference. This one provides more basic fundamental units. Let's practice calculating L. Just practicing calculating the angular momentum of an object or a system, etc. It says determine the magnitude, so I don't have to worry about direction, I just have magnitude, of angular momentum for the following situations. The first one is a point mass, and the second one is a dart with a meter stick. So this is an extended body, and so I'll have to use I omega for this one. With a point mass, I will use the point mass version of the angular momentum in order to calculate it. Part A is a point mass with a mass given moving at, I'm going to notice this as a speed because of the units, meters per second, at a distance 4.761 angstroms. You might not recognize that, but that's an angstrom. 1 angstrom is 1 times 10 to the negative 10th meters from the center of circular motion. Okay, so when I think about circular motion, it's moving in a circle at any point at a distance r away from the center of the circular motion, and the velocity will be tangential. And so when I look at this, I'm going to notice that the angle between the velocity vector, the momentum vector, you could consider both of those, they're in the same direction, and the radius vector is 90 degrees. So I can write over here phi equals 90 degrees. So then when I write out this equation, L equals R mv, I'll put in sine 90, and I'm going to remember that sine 90 has a value of 1. So to calculate this angular momentum, I need to take the radius of the circular motion, the mass of the point mass, and the velocity it's moving at. So I'm going to write these out. The radius is 4.761 times 10 to the negative 10th meters in SI. The mass, and you may recognize this if you've done a lot of work with atomic physics, it's the mass of an electron, 9.11 times 10 to the negative 31st kilograms. And the velocity is still in here. The velocity is 6 times 10 to the 6th. When you run this through your calculator, you get a value of 2.6022 times 10 to the negative 33rd kilograms meters squared over seconds, which is a small value. It seems like a small value, but is not trivial. We will see that in a few slides here. I come back to this concept. So that's how you calculate the angular momentum of a point mass, is this equation, RMV sine phi. Make sure you identify phi well in your problem. Often it is 90 degrees, but that may not be the case sometimes, so be careful. Part B is a dart sticks into the 70 centimeter mark of a 500 gram meter stick that is rotating about a point 10 centimeters from the end at a speed of 20 RPMs. Okay, there's a lot of information here, so let's write some stuff out. Seems like we have a small m is the dart. I'm going to convert that to kilograms right away. There's the mass of the dart. It sticks to the 70 centimeter mark of a meter stick. So I'm going to write down the big mass of the meter stick will be 0.5 kilograms, and I'm going to get a picture going as well. So here's a meter stick. And we're not spinning about the end nor the center of mass, so I'll put the center of mass in here. We're going to need to consider that. It's spinning at about 0.10 centimeters from the end. Okay, so here's 10 centimeters here. I'm going to note that this distance here I will call d. That little d is the distance from the pivot point to the center of mass. I'm going to need that for the moment of inertia. So let me write down d is, well, that's 10 centimeters. This is 50 centimeters. So there's 0.4 meters between the center of mass and the pivot point. The dart sticks to the 70 centimeter mark. Okay, so if this is the 50, then I can make this the 75 centimeter mark, and this is where the little m is getting stuck. That dart gets stuck there, and this distance here I will call a big distance d. That big distance d to the dart will be, well, let's see, from the 10 centimeter mark to the 70 centimeter mark, that's 6 meters. That's 0.6 meters. Okay, so I've arranged the information. I also have the speed here. It says 20 RPMs. I can't have it in RPMs. I have to have it in radians per second. So I'm going to take a moment here and convert 20 revolutions per minute to radians per second. So I can say 1 revolution is 2 pi radians. And I can also say that 1 minute is 60 seconds. And when you run this through your calculator, you get omega equals 2.0944 radians per second. I held 5 sig figs just to make sure that I have accuracy when I use this number later in my problem. Okay, so there's the omega. To calculate the angular momentum, I need I omega. And so let's start looking at that I value. That I value, notice that we have 2 objects in the system. We have the dart and we have the meter stick. So I total is going to be I dart plus I meter stick. And I'm also going to note that the meter stick isn't being pivoted around its center of mass, but some other point. So when I find I meter stick, I'm going to have to consider the parallel axis theorem. And so that'll be I of the center of mass of the stick, about the center of mass, plus this d squared. D is the distance from the center of mass of the stick to the pivot point, which we decided was 0.4 meters. From the center of the mass to the pivot point is 0.4 meters, little d. Okay. So the pieces of I total are coming together. I for the dart, well, it's a point mass. The moment of inertia of a point mass is mr squared, so I'm going to put in here m big D squared. Little m is a distance big D away from the pivot point, so there's that. I center of mass for a stick is 1/12 big M L squared. I'm going to note that L is 1 though, right? It's a meter stick. L equals 1. I can write that down somewhere for you. L equals 1. Plus D squared. We can plug in numbers for this. 0.06 times 0.6 squared plus 1/12 times 0.5, 1 squared, plus 0.5 times 0.4 squared. When you run all of this through your calculator, you get the total moment of inertia to be 0.3516. And the units is going to be kilograms meters squared. Kilograms times meters squared. That will be I total. So I have an intermediate value for omega and an intermediate value for I total. So I can just plug these into my calculator. I total, 0.3516. Omega, 2.0944. And multiply those two together, you get an angular momentum of 0.7364 with units kilograms meters squared over seconds. Omega, yes, kilograms meters squared over seconds. So that's how you calculate moment of inertia. We have to take into account some sort of inertial element, and we need to take into account some sort of speed, as well as the radius between them. Angular momentum is a foundational concept in all of physics, which you can see looking down this list here. It's related to torque in doing work. It's related to collisions in circular motion. We'll look at several examples of that. It's related to the motion of heavenly bodies when you have bodies revolving around each other, which brings us also to atomic physics when we think about electrons captured in an atom's electric potential. It's rotating, it's circling around that atom in some way. And even further in quantum physics, we see that angular momentum is a quantized quantity. It relates to orbital energies and shapes of shells. So if you're into chemistry and physical chemistry, this is an important concept, as well as spin of fundamental particles such as the electron, spin up and spin down. So we see angular momentum all over the place in the cosmos as a fundamental principle, and because it is a state function, momentum is a state function, we can conserve it, which is why it comes up in collisions and explosions. It allows us another way to access an event by just looking at the initial and final state of it without getting concerned about what's going on in between those two states. So we'll see that with conservation of angular momentum in the next couple of lessons. I wanted to focus in on the quantization of angular momentum as an application. In atomic and molecular systems, angular momentum is observed in discrete values. That's what we call quantized. And without getting into details, this relates to the de Broglie's wavelength and resonant frequencies for electrons orbiting atoms. The Bohr model of the atom provides a simplistic view of the inner dynamics of the most basic atom. We think of it as a nucleus with an electron circling around it, and this electron has some sort of radius. This is not an accurate model. This is not how electrons act at all, but it does make an accurate prediction about some of the physical quantities associated with this system. The most accurate model that we have at this point in time in physics and all of human history is quantum mechanical model, where the electron isn't even a point mass. It's some sort of wave that encapsulates the space around the other waves in the nucleus. Very complex. But when we look at the Bohr model, we think of a planetary model. There's a center, such as the sun, and the electron revolves around it just like the Earth would around the sun. N is an integer value. It could be 0, 1, 2, 3, all the way up to whatever we want. It's an integer. H is Planck's constant. This is a cosmological constant. The universe set this. It is fundamental in the dynamics. It's one of those constants like G equals 9.8, or the mass of the electron, or the Boltzmann constant, any one of those. And is given by this value. It has units joules times seconds. So that's how you calculate the angular momentum of an electron in the Bohr model, the simplistic planetary model of the atom. H bar is defined to be h over 2 pi, which you may see if you continue forward in physics. Just to simplistically apply this, let's look at the Bohr model of the hydrogen atom, a 1-1 hydrogen atom where there's one proton, which means there's one electron, and that's about as simple as you can get for an atom. An electron in the lowest energy state moves in a circular orbit of radius 0.529 angstroms around the proton. So I'll write that down. The radius is 0.529 times 10 to the negative 10th meters. An angstrom is 10 to the negative 10th. Determine the following quantities for the electron. Okay, orbital speed. So to me, that's the velocity. Kinetic energy. Okay, I recognize that. And angular frequency. This is frequency. And remember, angular frequency is related to the angular velocity in rotational motion. I'll also write down for us the mass of the electron. We're going to need the mass of the electron is 9.1094 times 10 to the negative 31st kilograms. Okay, so let's work on A, the orbital speed. The orbital speed here will be in the angular momentum. I know that I'm in the lowest energy state that's non-zero. It has to be non-zero. So the lowest energy state that's non-zero would be when n equals 1. And I have an equation for finding the angular momentum. L equals 1 h over 2 pi. Well, the electron is a point mass, so I'm going to use the point mass version of angular momentum. And so those two things have to be equal. And when I think about circular motion, I did this on the previous problem. There's the radius, there's the velocity. or the momentum, and the angle between them is 90 degrees. So I'm going to put phi equals 90 degrees here. So I get RMV. So the angular momentum in the Bohr model for the electron is given by this, and I can set it equal to that. L equals L. Let's solve for V equals H over 2 pi mR. I can plug values in here. I need a little bit of space because these numbers are pretty large. H is 6.626 times 10 to the negative 34th joules times seconds. I'm going to put this over 2 pi times the mass, 9.1094 times 10 to the negative 31st. And then the radius is 0.529 times 10 to the negative 10th. So when I run these through the calculator, numbers through the calculator, I get a value of 2.19 times 10 to the 6th meters per second, which is a pretty good speed. That's pretty average for electrons in an atom. Interestingly enough, I wanted to know what this was in some units that I recognize, and it's 1,360 miles per second. So when you think about electron in a hydrogen atom, it's moving around very fast in there. So that's that orbital speed. I've done that part of the problem. Let's move to part B, the kinetic energy. And the kinetic energy, you may want to knee-jerk and say 1/2 I omega squared. And we don't know omega straight off. We know velocity, but we don't know omega. The other thing is that we can remember that energy is related to the angular momentum. Just like energy is related to momentum, kinetic energy is related to angular momentum. So I can use this equation, L squared over 2I. Well, I know L. Same equation I used for the first part, H over 2 pi. I, for a point mass, is mr squared. So I can plug these things in. I get H over 2 pi, quantity squared, over 2 mr squared. I can plug these values in, 6.626 times 10 to the negative 34th divided by 2 pi, that whole quantity squared, divided by 2 times the mass of the electron, 9.1094 times 10 to the negative 31st, times the radius squared, 0.529 times 10 to the negative 10th quantity squared. When I run that through my calculator, I get a kinetic energy equal to 2.1813 times 10 to the negative 18th joules. If you know anything about the electron or how you look at energies of electrons in and around atoms, joules is not the preferred units. We prefer EVs, and it may not surprise you to see that when you convert this to EVs, you get 13.644 EVs, which we expect for an electron trapped in the potential of a single proton. Very good, very interesting. So there's part B. Let's move to part C. The angular frequency F, which is the omega term here, 2 pi F. Well, it seems like there's multiple ways to get to it. I wrote down L equals I omega. We could use that. We know that velocity equals omega r, and that may be the easiest one. For this electron rotating around, yes, it has an omega, and because the translational velocity is related to the omega, I can write this equation down, and I'm going to put in here what I know about omega is 2 pi times the frequency. So 2 pi times the frequency is omega times r. Well, I solve for the velocity. I have a value for the velocity. So if I solve for frequency here, I get the frequency equals the velocity divided by 2 pi r. That'll equal 2.19 times 10 to the 6 divided by 2 pi times 0.529 times 10 to the negative 10th. And when I run that through my calculator, I get 6.584 times 10 to the 15th times per second. Remember, a frequency, an angular frequency, is just how many times per second. And we call this hertz. 10 to the 15th times per second, the electron goes around in the atom. That's what that's saying.